Have you ever felt like your CNC drill was just fighting you? Like maybe it wouldn't power through certain
Yeah,
materials?
or the bits wear out way too fast.
Exactly. Or you just, you couldn't hit those really tight tolerances consistently. It's uh it's maddening when that happens.
It really is. You look at the specs, maybe the motor size, right? But then on the shop floor, the actual performance, it just doesn't seem to match up. There's this gap.
That gap, that's precisely what this deep dive is all about bridging. We've gathered a whole stack of sources you shared, articles, notes,
Lots of
research.
stuff in there.
Yeah, and our mission today is really to get to the absolute core of why some CNC drills are these reliable workhorses,
Mm.
you know, and others are just, well, headaches.
Constant problems.
We're unpacking the factors that the sources say truly influence performance and, importantly, lifespan.
And what really jumped out from all that research you sent over was how it consistently pointed back to two sort of fundamental things. If you have to boil it all down, it really comes down to the spindle and the machine structure itself.
Yeah, the sources call them the real workhorses, or they talk about this core dependency, get these wrong, and, well, you're right back to those frustrations we started with.
There's actually a great analogy in the material we looked at thinking about a high-performance athlete.
Oh, yeah.
Yeah, to be at their peak and have a long career, they need both things. A really strong heart and a solid skeleton.
Okay, I see where this is going.
In the CNC drill, the spindle is that heart, right? Delivering the power and the, let's call it muscle, the torque. And the machine structure, that's the rigid skeleton. It provides the stability, the accuracy.
Gotcha. So think of this deep dive as your shortcut, maybe, to understanding these really non-negotiable elements. We're trying to cut through the noise, show you what the sources say makes or breaks a drilling operation, going beyond just, the features list on a brochure.
Mm-hmm.
Okay, let's dig in.
So the central idea, the thread running through everything is pretty clear. A CNC drill's performance, how well it works day to day, and how long it lasts. It really hinges almost entirely on having a spindle that's properly matched to the work.
Matched how?
Matched in terms of delivering the right power and the right torque for the job. And then crucially, having that spindle supported by a machine structure that's rigid enough.
Rigid enough to do what exactly?
Rigid enough to absorb the cutting forces without flexing, minimize harmful vibration, and ultimately hold its precision over time.
And the material you shared, it didn't really pull any punches about this, did it?
Yeah.
It highlighted how learning this lesson the hard way,
Yeah.
buying the wrong machine is just incredibly costly.
Oh, absolutely. Years of fighting it, burning through tooling way faster than you should, maybe dealing with unexpected breakdowns.
Yeah.
It adds up fast.
Yeah, that downtime kills you.
Totally. If that spindle is undersized or maybe it just lacks the right characteristics for your work, you get those sluggish cuts, the excessive tool wear, maybe even stalls, which are just infuriating. And if the frame isn't rigid, well, then you're constantly battling accuracy problems. And those vibrations, they punish everything, the tools, the machine components themselves.
Okay, so let's tackle that heart first, the spindle. And specifically, let's talk about understanding its power needs. Like, if you've ever felt your machine just struggle, really laboring to push through a certain material.
Or bogging down on bigger holes.
Yeah, exactly. Bogging down on larger diameter holes.
Mm.
The sources seem to suggest it's a pretty clear signal you might not have enough spindle power for that particular job.
Yeah, that's one of the first things the sources really dig into. The spindle power you need isn't just some, big number on a spec sheet. It's a direct result of the material you're trying to drill.
Makes sense.
And the specifics of the hole you're trying to create.
Right.
The geometry.
The material properties specifically seems like a huge driver according to the sources.
Oh, they absolutely are. Just think about hardness and strength. Trying to drill through something tough like stainless steel or maybe titanium alloys, that requires way higher cutting forces compared to, say, soft aluminum or plastics.
Right.
So you just need more power, plain and simple, to overcome that resistance.
And toughness, that's different from just hardness, right?
Yeah.
That plays a role too.
Exactly. Some materials, maybe certain alloy steels, they're just tough. They generate a lot of heat. When you cut them, the chips get kind of sticky.
Right, I've seen that.
Yeah, and that whole dynamic environment increases the load on the spindle. So you need more power just to keep the cut smooth and stable without it, bogging down.
I noticed the sources also brought up thermal conductivity. How does that fit in?
Yes, that's actually pretty key, especially with materials like those titanium alloys again. They're poor heat conductors.
Okay.
So the heat builds up like crazy right in the cutting zone. That increases resistance, makes the tool wear faster, and the spindle needs enough power in reserve to handle those higher forces when things get hot.
Okay, so materials, hardness, toughness, thermal properties.
Hmm.
That's one big piece of the puzzle. The other major factor the sources kept highlighting was the hole itself. Its size, its geometry.
Absolutely. It sounds kind of obvious, maybe, but a larger hole diameter means you're using a larger drill bit.
Stands to reason.
And a larger bit, well, it has a larger cutting surface area engaged with the material at any given time. That generates proportionally higher cutting forces. The spindle just needs the muscle, the power, to handle the forces from the biggest bits you plan to use regularly.
And it wasn't just the diameter, right? It was also about cutting volume.
Exactly. If you're drilling bigger holes efficiently, you're probably using higher feed rates, maybe deeper cuts per pass.
Right, trying to get the job done faster.
Yeah. And that increases the amount of material you're removing every second, which puts a heavier, more dynamic load on the spindle. It needs the power to keep up.
The sources had some examples, didn't they, to kind of illustrate this?
They did, yeah. Just general examples, mind you, based on typical scenarios. Like for softer stuff, wood, plastics, aluminum. Drilling a small hole, maybe up to 5 millimeters, might only need, say, 0.8 to 1.0 kilowatts.
Okay.
And that's often done at really high RPMs, maybe up to 24,000. But then if you go to a medium-sized hole, say up to 16 millimeter, in those same soft materials, you could easily need 3.5 to maybe 6.0 kilowatts, still often at high RPM.
Wow, quite a jump. And what about for harder materials, steels and alloys?
Yeah, the jump is pretty significant there. For maybe a 10 millimeter hole in steel or a hard alloy, you might be looking at 3.0 to 4.0 kilowatts. But notice, typically at much lower RPMs, perhaps around 15,000, maybe 18,000 RPM.
Okay, lower speed, more power needed for the size.
Right. And then scale that up to, say, a 20 millimeter hole in that same hard stuff. Now you're potentially looking at 7.5 to 10 kilowatts, or maybe even more. Still in that lower RPM range generally.
Wow. Yeah, seeing those numbers, even as examples, really hammers home the difference that material and hole size make. And it's good the sources stress these are just illustrative, right? Not hard and fast rules.
Absolutely. The exact numbers will vary depending on the machine design, the specific tooling, the process, but the underlying principle, that's consistent across all the research. The key takeaway for you, the listener, is thinking about your specific materials and the largest holes you plan to drill regularly. That's how you ensure you've got the right horsepower from the get-go.
Okay, so that covers power, the sort of raw horsepower aspect.
Yeah.
But the sources put a huge emphasis on something else, too. The spindle's muscle, as you called it earlier, the torque.
Ah, yes, torque.
Yeah, if you've ever heard that just awful chattering sound.
Yeah.
Or felt the drill bit kind of hesitate. Or even completely stall out when you're trying to make a bigger hole, especially in hard metal. The sources point to that often being a sign of not enough torque.
That really is the other side of the spindle coin, isn't it? Torque is that rotational force, the twisting force. Yeah. And it's absolutely critical, especially at the lower RPMs you often use for drilling large diameters or tough materials.
Why especially then?
Because that's when the cutting resistance is often highest. Torque is the force that has to overcome that resistance from those big bits and hard stuff. Enough torque means stable cutting, and it prevents those stalls that just stop you in your tracks.
Yeah, the sources had this point that really stuck with me about torque being the muscle behind the speed. They even share that little story.
The Forstner bit one.
Yeah, about a spindle that had plenty of horsepower on paper, but it struggled with a large Forstner bit in wood at lower speed.
Ugh.
Why? Because it had tons of power at high RPM, but it just lacked enough torque down in that lower speed range.
That's a perfect illustration of the difference. You absolutely need adequate twisting force delivered at the specific RPM you're actually using for that cut. And, spindles and their drives, the VFDs, the variable frequency drives, they really vary in how well they maintain torque at lower speeds.
Oh, okay.
Some are specifically designed, engineered even, to deliver high torque even when they're spinning relatively slowly. Others tend to drop off more.
What else influences the torque you actually need, according to the sources, beyond the spindle's own characteristics?
Well, besides the material's inherent resistance to being cut, what they called the cutting force coefficient, which is higher for harder, tougher stuff.
Right.
And the really obvious factor of the hole and the drill bit diameter bigger means significantly more torque needed. The sources also mention how things like using proper cutting fluid can make a difference.
How so?
Good lubrication reduces the friction between the bit and the workpiece. Less friction means the spindle doesn't have to work quite as hard, doesn't have to deliver as much torque to make the same cut smoothly.
It sounds like having enough torque, it's not just about, managing to drill the hole, but about the quality of the whole process.
Exactly. The sources laid out several really non-negotiable benefits. First off, processing quality. Sufficient torque gives you a stable cut. That reduces vibration, reduces noise, and that leads directly to better hole accuracy and a much smoother surface finish.
And I guess that stability also ties into, like, equipment safety and how long the machine lasts.
Absolutely. Preventing those stalls and that really violent chatter means you're avoiding sudden shock loads on the machine components.
Ah, makes sense.
It reduces excessive noise, too, and minimizes the risk of damaging the spindle bearings, the gears, other parts over time. It's about longevity.
Plus, it sounds like it's a huge factor in how long your tools last, your drill bits.
Oh, massively. When the spindle delivers consistent, adequate torque, the drill bit cuts efficiently, smoothly. It's under less stress compared to a bit that's constantly struggling or chattering.
So they just last longer.
They last significantly longer, and good drill bits aren't cheap, right?
Definitely not. So the big takeaway here seems to be, look beyond just the peak horsepower number. You need to make sure the spindle has the necessary torque profile, especially for your toughest jobs, at the RPMs you'll actually be using.
Precisely. That's the key message on torque.
Okay, so we've dug into the spindle, the heart, and the muscle. Let's shift gears now to the skeleton of the machine. Yeah, the frame rigidity. If you've ever looked at a CNC machine and maybe thought, that looks a bit floozy, or maybe you've really struggled to hold tight tolerances on critical parts, the sources trace a lot of those kinds of issues back to the machine's underlying structure.
Yeah, the machine frame design, it's absolutely foundational. The sources really emphasize that its rigidity, meaning its ability to resist bending and flexing when those cutting forces hit it, and also its ability to dampen out harmful vibrations. Those two things are just paramount for the machine's performance and accuracy.
And the consequences if that rigidity isn't there, according to the sources.
They're pretty significant and usually costly. Things like drastically reduced tool life.
We keep going back to that.
Because it's true.
Yeah.
Also, inaccurate parts that might fail inspection or just not fit right. And of course, a poor surface finish on your drilled holes.
So how exactly does rigidity help guarantee that precision we need?
Well, a rigid machine basically maintains its geometric shape, its integrity, even when it's facing pretty substantial cutting forces during drilling.
Okay.
That means the drill bit stays precisely where the control system intends it to be. That ensures accurate hole positions, accurate sizes. The sources also mention that a lack of rigidity can actually cause the whole frame to deform slightly under load.
Just slightly.
Even slight deformation directly impacts the accuracy of the final workpiece. They even noted that poorly designed frames can be more susceptible to accuracy shifts just from temperature changes in the shop.
Wow. And vibration sounds like the big enemy rigidity fights against.
It really is. Vibration is just incredibly detrimental in machining. The sources highlight all its negative impacts, ruining surface finish, dramatically accelerating tool wear,
That is again.
shortening the machine's overall lifespan because components are getting shaken constantly, and causing that awful chatter noise, which often indicates poor cutting conditions.
So how does the actual frame design combat vibration based on the material you look through?
Good design actively tries to minimize and absorb vibration. Part of that is using materials with inherently good damping properties. Cast iron is often favored because it offers a good blend of stiffness and damping.
What about steel frames?
Steel frames are very stiff, but sometimes they might be enhanced, filled with something like epoxy granite, for instance, specifically to boost their mass and damping capacity. Beyond just the material, the sources mention specific design elements.
Like what?
Things like dynamically balancing rotating parts, strategically placing support points for maximum stability, and sometimes incorporating specific damping measures or pads right into the structure itself.
It's also worth remembering the environment, right? The sources mentioned the floor.
Yeah, that's a good point. Even the floor the machine sits on matters. A solid, well-supported concrete floor helps minimize external vibrations from traveling up into the machine and affecting the cut.
And the material touched on static versus dynamic rigidity, briefly.
Yeah, just briefly. Static rigidity is about resisting steady forces, like the constant push of the drill. Dynamic rigidity is about resisting vibrations, those oscillating forces. And for a drilling machine, really, both are crucial. You need both.
So it's really not just about making a machine heavy, is it? It's about engineering that mass, that structure, for maximum stability and vibration resistance.
Precisely. And that stability, that rigidity, it isn't achieved by just one single large piece. The sources really break down how it's more of a team effort. It comes from several key components all working together effectively.
Okay, that's a good transition then. Let's move from the overall idea of frame design to the specific parts that actually build that rigidity as the sources laid them out. They listed things like the heavy machine bed, a sturdy column, a robust spindle assembly, precise guideways, and even mentioned assembly techniques.
Right. And you have to think of it like a chain, really. The overall rigidity of the whole system is only as strong as its weakest link among all these components.
Makes
So the machine bed, or the base, that's the absolute foundation. It supports everything else, and its mass helps absorb vibrations. The sources describe it as often being heavy cast iron or maybe engineered steel, specifically designed with internal ribs for stiffness, perhaps filled with that epoxy granite for extra mass and damping.
Then you've got the column, or the main frame structure, the upright part.
Exactly. That's the pillar, basically, that supports the spindle head. It has to resist all the side forces generated during drilling without flexing. The sources note that good columns are often box-shaped, or they feature extensive internal bracing, and they're built from high-quality, stable materials to prevent twisting or bending.
Okay, what about the spindle assembly itself? We talked about its power and torque, but structurally.
Structurally, it's absolutely central to the machine's precision. It holds and rotates the drill bit accurately. So the sources highlight that a robust spindle shaft and high-precision bearings are key to minimizing runout, that little wobble. And the housing it sits in needs to be really rigid, often made of cast iron, maybe even integrated directly into the column structure for maximum stiffness.
And then there are the parts that handle the movement, the linear motion systems, the rails and guides for XYZ.
Absolutely critical. Those guideways, whether they're linear guides or traditional boxways, they're usually made from hardened steel. They have to resist deformation while allowing that smooth, controlled motion. And one thing the sources specifically flagged as essential was proper preloading of these guides and the bearings.
Reloading, what's that do?
It basically removes any tiny bit of play or clearance in the system. It makes everything much tighter, significantly enhancing stiffness. And that directly impacts the machine's ability to hold position accurately during the cut.
So beyond these big structural pieces, the sources mentioned assembly details playing a role too.
They did, yeah. Because even if you have the absolute best, most rigid components, if they're not assembled correctly, if bolts aren't torqued to spec, if guideways aren't perfectly aligned and preloaded the way the designer intended, you just won't achieve the rigidity you paid for.
Yeah, the execution matters.
Hugely. Preloading those bearings and guideways correctly is vital for minimizing any backlash or slop and maximizing the overall stiffness.
And finally, they touched on some features that aren't strictly structural, but still contribute to stability in a way.
Yeah, things like coolant through drilling capabilities. Now, that's not part of the frame itself, obviously, but by efficiently flushing chips out of the cutting zone.
Right, from inside the drill bit.
Exactly. By doing that, it actually reduces the cutting forces needed and can significantly decrease vibration during the process. So indirectly, it improves stability and helps tool life.
So stepping back and looking at the whole picture, it's clear that from that heavy base, providing the fundamental platform, all the way up through the column, the precise guides, the robust spindle mount, every single part of the machine structure plays a critical role in creating that stable, accurate environment needed for good drilling. A weakness anywhere really compromises the whole system.
It's definitely a system where every component's contribution matters, no doubt about it.
So let's try and bring this deep dive full circle then. Based on all the source material you provided, it seems pretty undeniable, really. The core capabilities of a CNC drill's spindle, its power, yes, but especially its torque profile for the specific tasks you do and the fundamental integrity of its structure. The rigidity of the frame, the components. These aren't just like marketing bullet points.
Well, not at all.
They are the absolute non-negotiable heart and skeleton. They determine its real-world performance and, frankly, how long it's going to serve you well.
And getting those core elements right, which is what the research really hammered home, leads directly to the good stuff. Better quality parts, tools that last longer.
Less frustration.
Less frustration, definitely. And just a more reliable machine overall, one that works with you, instead of feeling like you're constantly fighting against it.
Yeah. And hopefully, understanding these foundational elements, drawing from the source material like we did today, gives you, the listener, a much deeper insight into why a machine behaves the way it does. Whether you're, evaluating a potential new purchase or maybe just trying to troubleshoot issues you're seeing on the shop floor right now.
So maybe a final thought to leave people with. Now that you know the fundamental roles of the spindle's power and torque, and the crucial importance of the structure's rigidity, what does this actually mean for your next decision? When you're evaluating a machine, or even when you're troubleshooting problems you might be facing today, how would you prioritize these core elements, knowing what you know now, based on the specific materials and the types of holes you work with day in and day out?